Here is problem number 2 in sample test 3. Consider the circuit shown was the equivalent resistance of the network. For looking at the resistance of the network, we want to look for parallel and series combinations first, and we probably want to work our way in toward the battery. So looking on the outside, we have a series combination of this 3 with the 4 and the 3 here, all in one line. 3 plus 4 plus 3 is 10. So if we add that series combination, our circuit is going to look something like this. With this 10 on the outside here. Oops. I didn't need 10 on the outside. I have a 10 here. We have a 3, 10, 2, 5, 5, and then 28 volt battery. Alright, now on the outside we've got a parallel combination of a 10 with a 10, and there's two of them. So our R parallel is going to be product over the sum, which would be 10 times 10 over 10 plus 10, 100 divided by 20, or 5 ohms for that. So now our circuit looks like this. With a 5 on the outside here, a 2 here, 3, 10, 5, 5, and then our 28 volt battery. So now we have a new series combination with the 3, the 5, and the 2. That adds up to 10. And adding those together, our circuit now looks like this. With a 10 on the outside, a 10 here, 5 here, and down below here another 5, 28 volt battery. This 10 is in parallel here with the other 10. We've already determined that that should be 5 ohms from a parallel combination. So our circuit now looks like this. 5, 5, 5, 28 volt battery. And now we have a series combination. 5, 5, 5 adds up to 15. And so our final circuit looks like this. 15 ohms, 28 volt battery. Our R equivalent is 15 ohms for the whole circuit. Sounds good? So that is part A. B, what is the power supplied by the battery? Well, let's find the current coming out of the battery. That's equal to the voltage of the battery divided by R equivalent, and that would be 28 divided by 15, and that is equal to 1.87 amps. That's the current coming out of the battery. So the power dissipated by the circuit, which will be the power supplied by the battery as well, would be equal to this current squared times the equivalent resistance of the whole circuit, and that's going to be 1.87 squared times 15 ohms, and that is equal to 52.3 watts, joules per second. Same thing could have been found using V squared over R. So if you had said 28 volts squared over 15 ohms, that should also come out to 52.3 watts. What is the power dissipated in the 2 ohm resistor? figure this out, we need to do I squared R for that 2 ohm resistor. We need to know what its current is. Now if we look back at one of these representations, which all these representations are equivalent for the circuit, if I look at this one right here, I got 1.87 amps coming into this junction and splitting through one 10 ohm resistance and another 10 ohm resistance. And we could do current division, opposite resistor over the sum of the resistances times the current coming in. But if you did that, you would find that the current would split evenly over these two branches. So the current that's going into each branch is half of 1.87. So the current going into that branch is 1.87 divided by 2, which would be 0.933 amps into each branch. And that branch of the 10 ohms is actually the same branch as the 3, the 5, and 2 in series. So each of those individual resistors will get that same current of 0.933 amps. So the power in the 2 ohm resistor is going to be its current squared times its resistance, which would be 0.933 amps squared times 2 ohms, and that is equal to 1.74 watts. So that is the power dissipated in the 2 ohm resistor, 1.74 watts.